All right, here's the deal. Hold on, here's the deal. I think basically every sport has nuances that people who don't follow that sport don't understand. So it looks very simplistic. So, for example, like for me, if I'm thinking NASCAR, aren't they only just changing turning right all the time or turning left all the time, whatever the direction is. But I feel like every sport has nuances that only the fans of that sport get. So, like if you're a football player, you understand, especially if you're on the line, that there's a lot of like footwork and stuff like that that's involved for that translates into like important skills, not hey, it's a bunch of big guys trying to kill each other. There's nuance in there, details that make one 300-pound linebacker as fast or faster than a guy who's way lighter than him or something like that. So I think most sports are significantly more skill based than people who don't play those sports recognize.
Here's my argument that I'm not even talking about the footwork. If you look at the play design, there's so many different play designs.
Well, I'm not just talking about footwork either. I'm just talking about the sport as a whole. There is details and nuance that make it more complicated than people give it credit for. Yeah. Golf. Golf is a good example. Golf is not just about hitting the ball. Golf is also about reading the lie. How's it sitting in the grass? What kind of stuff is it? Is the ball going to spin? What's the wind doing? Temperature outside? There's all sorts of variables that go into hitting a golf shot that are far beyond the physics of swinging and hitting the ball. Baseball, the same thing. I mean, the amount of time you have to hit a pitch in baseball is like next to no time. When these guys are throwing 100 miles an hour. So, these guys are having to not just time, but recognize change ups and curveballs and things like that when they basically have no time to make decisions. That skill is a skill that normal humans don't have. So there's this high learning curve on any of these professional sports that I think people who don't play them don't appreciate. Yeah, I heard a comedian recently make some joke that sounds right. It's like, when you get a bunch of guys together, like every guy has that story where if just one thing would have went different in their high school, they'd be playing professional sports or something like that. We all have that story. If only I hadn't twisted my ankle, I was going to Bama. All right, so let's dive into recursion. So we talked about Linux Hello World. We reminded ourselves about compilers and crap like that, and how a compiler translates from a high-level language to a low-level language, but it needs to know both the architecture it's going to, that is the language the processor speaks, and it also needs to know the operating system the program is going to run on, so the compiler can take advantage of the built-in system calls or API calls for the operating system that it's targeting so that it doesn't have to write 4 zillion lines of assembly code when it compiles. It only has to write the minimum amount of lines to communicate with the operating system whenever it can, which then in turn communicates with the CPU. So that software, the software to write something to the screen has already been written, so your compiler doesn't have to rewrite that in the assembled file. It just has to call upon that particular operating system's ability to do that. Make some sense? So we've added a layer of organization to even our low-level programming. Why reinvent the wheel? Every single program doesn't have to have all of the nuance for talking to a monitor on your computer by way of the CPU. It can leverage the operating system that's running on there to do it for them. Presumably, the operating system maybe had to make some specialized decisions for some things. I mean, writing out to the screen, maybe not. That's been around for a while, but possibly something with network communication, or possibly something with displaying graphics on the screen through a dedicated GPU. Sometimes those things are better handled by the dedicated drivers for your GPU or something like that, rather than some lowest common denominator assembly program. All right, so something for us to keep in mind how we ultimately get to an executable. Okay, from our perspective as computer scientists, we're all about typing in high level code, either compiling it and running it, or that doesn't even happen that much anymore. Now we just hit the little play button, right? And that compiles and runs it. So we're actually not visually seeing a step. If you're actually running Java code from the command line, you would first compile it using a command called javac, Java compiler, and that would turn your .java file into a .class file. That is your compiled version of your Java program. And that .class file has a low-level language built into it. It's in binary format, but it has a low-level language built into it called Java bytecode. Okay, and the competitor to Java bytecode from Microsoft is called what? Missile code, Microsoft Intermediate Language. So .NET programs, when you compile them, they create a file that's filled up with missile code, which then at runtime, when you first run that program, it takes just a little bit longer because Windows, I mean, C Sharp is a platform independent programming language, just like Java. So Java's platform independent. You write your Java program once, it'll run on any computer that has the Java virtual machine. So Sun Microsystems, now Oracle, they wrote a program called the Java Virtual Machine, which is basically a computer written in software. It's a software-based CPU, and it's a software-based pseudo operating system. So your Java program is compiled in terms of that. And then that program was written specifically for Windows or for Mac or for Linux. And it then translates to the way you do file IO for that particular operating system, or the way you do network calls, or the way you talk to the display. So Java has a layer in the middle, but that program had to be translated for every single, or ported is usually what it's called, had to be ported to every platform that they wanted to run Java programs. Okay, so we would say Java is platform independent. We can write our program once and it'll run on any of our modern operating systems because they've all had the Java virtual machine ported to them. All right. So in the early days of Java, that was one of its claims to fame, is the idea that it was a platform independent, because back then the Mac people, as usual, are screaming and whining really loud, right? Because all the video games and important software was coming out for Windows and not for Mac, and us important Mac people are being ostracized or whatever when 98% of the install base was Windows. So if you're a company making software, especially back then, where writing software was and selling it was difficult. You had to go and negotiate all this stuff. It was like publishing a book. You had to get it on the shelves at Best Buy and stuff like that. You weren't downloading software at a whim. You had to, there was gas involved and then installation discs and all sorts of stuff. Way back in the day, you had installation floppies, where it's like install Windows 3.1 from floppy disk. I think there was like maybe 15 or 16 disks. It would say, please insert disk 7. And then it would sit there with the slow floppy disk, the 3.5-inch floppies. It would sit there and cook on that for 10 minutes or something. And please insert disk 8. So it would be this big long process. Most operating systems came on a single CD for a while, which is 640 megabytes is the maximum size of a CD. Then you had DVD distribution, but pretty quickly around then is when stuff started being distributed over the internet. But in any case, Java, platform independent. It was kind of the answer to the Apple people saying, we want all the cool software that all the Windows people get. We want it to run on our computers too, because we're obviously running the superior operating system because we're Mac people and we're better than you. That's the mentality, right? They were screaming. The Java people, or Sun Microsystems back then, they wrote this with the idea of appeasing, or at least in part, with the idea of appeasing the screaming Mac people. But then what happened? Well, plenty of software could now be written that takes advantage of platform independence. You write it once, it'll run on anything. But things like games, you know, something like Angry Birds, fine. It'll run on both Java's high enough performance for Angry Birds, but you're not writing Call of Duty in Java. There's too much stuff going on, too much. You don't want that translation layer, even if it's fast. You want to be running on direct hardware as much as you possibly can. Okay. Well, so Microsoft then tried to steal Java, right? They had a product. Anybody know what Microsoft's version of Java was called? Came with Visual Studios. I think it was still on there in Visual Studio 6.0. Well, it was. You want to take a guess? Back then they had. Shouldn't you memorize everything that comes out of my mouth? Even the stuff that's off topic. You never know when I might forget I asked stuff on tests that I assume I mentioned that I never did. That's how do you think I learned to start going back through my slides? Instead of like, what should I have taught before midterm or final? It's what did I actually talk about? That's why you sometimes get Ninja Turtles and stuff on there. That was 3 classes worth of material. We can't skip that. Oh my gosh, absolutely. All right, so it was called J++. Yeah, so Microsoft had a product called J++, which was Java syntax, and it was, oh, that's something solid. What is this? No. So they had a product called J++. It was Java syntax, but it ran on top of Microsoft's Java virtual machine. So Microsoft wrote their own Java virtual machine specifically for Windows. And it was kind of thought back then that if you were writing Java code to run on Windows, it was in your best interest to use the Microsoft version of the Java virtual machine because it did a couple of things a little bit quicker because Microsoft was able to take advantage of some operating system stuff that was not necessarily publicly available. Makes some sense, whatever. Well, but they didn't just steal Java from some kid who's working out of grandma's basement. They stole it from Sun Microsystems. And I know most of you maybe have never heard of Sun Microsystems or maybe just kind of vaguely have heard of it because it hasn't been a company since most of you were born. Oracle bought it many, many years ago. Oracle must have bought it 20 years ago now or something like that. Maybe it's 15 years ago, but a while. So at the very least, you were young, too young to care. So they bought it. But Sun Microsystems was a major, major tech company in Cupertino, California. And they sued Microsoft. You know, this is not a time. I mean, Microsoft was the big boy. So they weren't Microsoft size, but, you know, they were like Intel size. This is a major, major, major company. So they went to war with Microsoft. Sun Microsystems won the lawsuit. Microsoft then comes out. They had to stop selling their J++. They come out with a brand new, I mean, this was built from the ground up. Okay. They didn't use one inspiration from anything else. They came out with C#. Okay. So with C# is, you know, C++ with the pluses moved. So now it's a sharp, you know, with the, so, in C#, I think I've mentioned it at least at some point where I was at the ACM conference at the University of Illinois when they first announced C#. And back then, so this must have been right around the year 2000 or something like that, ballparky, right in that zone. So whenever you go to one of these conferences, all the big boys showed up to the ACM conferences. The two big things in technology are ACM and IEEE. Everything else is B League. So, you know, that's your Major League Baseball. Pick your favorite sport. That's the East and West or the NFC North or the, you know, these are major, major, major things. So people would go, the big boys would show up at every single one of those conferences. So I went to the ACM one with a couple of students at the time. And you always go to Microsoft's thing because Microsoft's giving out the best free stuff. Everybody else has like the stress balls or the bouncy balls, you know, whatever it is, like stupid stuff. Microsoft was giving out sealed boxes of Visual Studio 6.0. It's like $500 software. that we had already all pirated off of online. This is in the early days of online. I am not that we were doing it as an ethical example of what you shouldn't do.
Sure thing.
Okay. So no, we stole it. Yeah. Yeah. I'm saying that you shouldn't do that. We were in the error. We were in the wrong. With $500 is $500. So anyways, we're going there. They're handing out $500 box software. And so we all sold it on eBay. This is early days of eBay. eBay was just becoming popular. Yeah, so we all made a buck off of that. But it was at that where they announced C# and those guys up there, and I had been programming in Java since like the language came out. So I was very familiar with the language, and he's describing all the latest, greatest stuff in C#, but he's just describing Java with different syntax, which is okay. Because I've taught through coding 1 and now into coding 2 that the language doesn't matter, right? Programming is the skill set. And we've seen that all of our languages took inspiration from the languages before it. C++ is built in terms of C. Java is built in terms of C++. C# is built in terms of Java. We can say, yes, it felt closer than it should be. Yes, it was the result of a lawsuit, but Microsoft did bring some stuff to the table that Java did not have. It's not like they had no innovation in C#. But some of the innovation was funny. So back then, even though we don't really talk about it much today because we don't see that need for cross-platform stuff for a majority of our applications. But back then, that whole Java is platform independent was a big deal. People really focused on that. So Microsoft comes out and says, oh yeah, C#, it's one of our .NET languages. It's platform independent, just like Java is. It'll run on any platform that supports the .NET component architecture, just like Java will run on any platform that supports the Java virtual machine. They're both saying the same thing, right? The difference being is all platforms supported the Java virtual machine at the time because Sun Microsystems had already written it for all the different operating systems. But when they say it'll support any platform at all that supports the .NET component architecture, which was only available on Windows, basically they're saying it'll run on any platform as long as it's Windows. And that's what they were saying. Hence the birth of the project called Mono. Anybody ever done anything with the Mono project on Linux? Well, you've probably done it with your stupid Linux crap. That's not actually stupid. I started doing Linux was my first operating system that I learned off of.
Linux is superior. It's the year of the Linux desktop.
You want to take a bet on that? Well, what does it mean to be the year? I'm a big Unix fan. I mean, I use terminal. If I just flip here real quick, I mean, I push my own operating system. So you see, I use terminal all the time, and I wrote a script here that pushes to the server that it's in, changes all the permissions, stuff like that. But, so I'm a big Unix terminal fan, no argument here. But when you say it's the year of Linux desktop, what
does no one knows what it means?
A long time ago, Walmart started selling computers that seemed cheaper, and they were running a version of Linux. You know the name of the distribution?
Wallowas?
No, it's called Lindows. Lindows was Linux that looked like Windows that Walmart could sell as cheaper computers because they weren't having to pay the license fee to Microsoft, right? Yeah, and clearly that really took off.
Yep.
Linux desktop but that's good. It's actually good for you and I and other people who are comfortable with command line. We don't want Linux desktop to become everybody's go-to. Most people need an operating system that is convenient to use, even if they're trading off some power. Where us as computer, yes, but it's never going to be as convenient as Windows or Mac OS because the software developers are creating the package to make them idiot proof, right? Where Linux, they're creating software for people who they already know are fairly advanced users. They don't have, I mean, if you're installing an RPM or a dep file, or you're, installing right from apt-get or, Yum or whatever, pick your package manager. Yeah. So, well, okay. So if you're going back to old tarballs and you're compiling yourself, which is fun, right? But that's not something that grandma's going to do, right? That's not something that your little brother is going to be able to do. So most of our operating systems are meant to be easier and easier and easier to use, and they abstract the details from the user. That's good. We want, especially for us, we're computer scientists. We want the world using computers, but we want to hold the monopoly on the deep knowledge, what's actually happening under the hood. A computer scientist could benefit from becoming very proficient with something like Linux, because Mac runs on top of Unix, which is the same thing as Linux. Literally, it's the same thing as Linux. Windows, yes, it runs on top of the NT kernel, but now it's already out now. I don't know if it's been adopted heavily yet, but now there's a Linux subsystem you can install for Windows. So effectively, Windows has created a mechanism for power users, something that replaced PowerShell. So PowerShell was kind of Microsoft's like, hey, here, go have some fun. And now they said, well, you know what? There's been something around for a really long time that can talk directly to the operating system and let you do things, and it's Linux. So they give you a Linux subsystem in Windows so that you can do the skills you learned maybe from using an operating system like Linux, but in an atmosphere where you could also download, the software that you want to get, and it's just ready to go, rather than having to wait for the source code to come out for Linux, or for you to go find the source code somewhere that was meant to compile for, let's say the Mac or for Windows. And now you got to go through and figure out what flags do I need to throw in here to get this thing to technically compile here. And am I going to have to run it through an emulator? Maybe, maybe not. Those are fun exercises, but not something grandma's going to do, right? So this is not the year of Linux desktop is what we're coming down to. And that's good for us.
If the amount of Linux users increase more, then more software companies would have reasons to make software.
People have been saying that since I was young. When the lab was, messing around with the different Linux distributions back then, Slackware and Gentoo Linux was the first Linux that came out where you could actually do your own bootstrapping. You actually compiled the OS as part of the install. It was you would compile for days. Because back then the computers were like 486 DX2 66 megahertz computers. They weren't 5.2 gigahertz turbo with 8-core processing. It wasn't that crazy stuff. Yeah, so Linux is not the year of Linux desktop. It's going to continue to be the year of Windows desktop with a little bit of Mac and a tiny sliver of Linux. Where you're going to see where you're going to see a possible turnover is when we move into the mobile operating systems, because you're already seeing that Windows is never going to lose their position as the most installed desktop operating system, but they very well might lose their position in fact, they already have lost, well, they never had the win for mobile-based operating systems that are now being bent to be the standard operating system. Apple has been selling their iPad Pros under the guise that, oh, this is basically a laptop. You get your keyboard and everything with it, but the operating system is not a laptop operating system. You can't just run some program you used to run. So there's a place where you still need a laptop or a desktop versus these tablets. You've had, how many of you had Chromebooks in high school? Okay, so Chrome doesn't run Windows operating system, right? What operating system does Chrome run? Chrome OS, which is the Chrome web browser. So you all went to school running something non-Windows with your little stupid laptop-like looking things that just ran a web browser. and that's okay. But we're seeing Windows losing its shine. Windows is not going to lose the desktop margin. What's going to happen is that world is going to disappear, just like VCRs disappeared, and we moved to DVDs. Nobody has a VCR anymore yet. Back in the day, having a programmable VCR that you could set to record multiple shows the same day was like, that doesn't exist. You're lying. The debates about VHS versus Betamax. There were fistfights over that, where most of you don't even know what I'm talking about. Oh, yeah. There had to be fistfights outside of Sears over that.
Oh, yes, years.
I bought a computer at Sears way back. All right. So, in any case, let's talk about recursion. We asked the question. Recursion is when a function calls itself from within itself. We're going to say some problems lend themselves to being solved recursively. Now, that last sentence is an important thing for us from the perspective of problem solving. We do not want to look at recursion as an upgraded tool, just like we don't look at object-oriented programming as necessarily being an upgrade to procedural programming. Sometimes procedural programming still makes more sense. If you ever are looking at jobs or internships and you're seeing things about like embedded programming, or systems programming, a lot of times, like for instance, you have a dishwasher at home, and the dishwasher has all these buttons on the front of it, right? Same thing with your washing machine for the clothes. It has all these buttons in front of it. Well, those are the inputs for a tiny little microcontroller that knows how to do the 11 things your dishwasher knows how to do, right? And it has a little tiny program associated with which tells it, okay, we need to turn on the fill with water cycle. We need to turn on the spinning jetty thing. We need to turn on the hot water, the cold water, the whatever it is, blah, blah, blah. It's a computer program, right? But it's running on a simplified operating system, a microcontroller that just knows how to pull those strings. All right. And when you go and look at embedded systems and you find out, well, which microcontroller does this run? How many of you have done anything with like Arduinos or any embedded system type stuff? So when you go out and when you download the Arduino software, you get to select your board. How many boards are in that drop down? A lot. Okay, we'll round down. There's a lot of boards in there. What's the difference between each of those boards? When you think about programmable microcontrollers, it sounds real techy and geeky and stuff like that, right? We got boxes of some of that crap back there. What's the difference between those different boards? Well, one difference is what's on board. Does it have USB support? Does it have Wi-Fi built in? Does it have Bluetooth? How many things does this board come with bolt-ons, right? Okay, if you rip all those bolt-ons off and you're just talking about the lowest common denominator, it is a microcontroller board with nothing extra. What's the difference between one microcontroller and another microcontroller? When we say microcontrollers, we're kind of wrapping our mind around what is a computer really? At the end of the day, a microcontroller compared to another microcontroller, what can one do that the other one can't? Okay, well, they all could take in certain inputs and take in certain outputs, but what's different between two different microcontrollers, or what might be different between two different microcontrollers in terms of inputs and outputs? Okay.
I mean, I guess they all have the same functionality, but maybe one might have less than the other.
Less, when you say functionality, less of what?
Less like versatility, much bigger.
Okay, yeah. Now I tried to throw you some bones. You're just making crap up at this point. Well, okay, it's not as bad as Carnival back there. Go ahead. Amount of inputs. So at the end of the day, the difference in these microcontrollers is how many things can they control? When we send a signal to pin 1, we're saying turn feature A on or turn feature A off. Feature A could be water spraying stuff. Feature A could be blow dryer stuff, whatever it is, right? Feature A is some pin that controls something. Well, then you have feature B, another pin that controls something. Some features might be complex enough that they require more than one input output in order to control. Maybe you have one thing that controls temperature and another thing, whatever it is. But bottom line is the difference between these different microcontrollers is how much power is in this thing in terms of how many different things can I control at once, right? How many things, and when we say control at once, what we're really talking about is just turning things off and on. Because what you buy is these, already made circuits. It's like, oh, I need a sensor that tests whether, there's moisture. So somebody makes a sensor that, fires a 1 if it detects moisture, otherwise it doesn't do anything. Well, so you take that, you plug it into your project, and now you are reading inputs from that for when it starts screaming about water, you might then have a sensor over, an output here where it says, if this input's screaming about water, this output needs to turn on the fan or alert the people to bring the mop, whatever it is. That's what microcontrollers do. Turn on and off different features and things like that. So your microcontrollers have more or less inputs in each other, which then typically translates into what processor is on them. Okay. Now, is a faster processor always better than a slower processor? What does it mean for a processor to be faster? Well, not all faster processors use more energy. If you're dealing with a newer processor, might use less energy than last year's processor, yet it might technically be faster just because of architectural improvements. But typically the job of a processor is to fake us out, right? We, the user, need to be convinced that everything is happening at once. It's happening so fast, all these cycles and stuff, that we believe that this superpower, this processor, has us covered, right? Now, if you're only controlling 3 things, you don't need as fast of a processor to fake us out. So a lesser processor maybe takes less energy, probably is cheaper to produce, especially if they're buying it in bulk. And things like that. So they don't necessarily take the fastest processor to put it on something that's only controlling 4 things. They will put a processor on there that is fast enough to convince the user that all those things are happening at once, just as the bigger boy will also be fast enough to do that. But it's going to save you a bunch of money, probably energy and all this stuff, to have this minimum processor that is fast enough to keep you tricked. Does that make some sense? So faster isn't always better. It depends on the problem it's trying to solve. Always use the right tool for the job. Go ahead.
You say referring to recursion functions or just like the concept in general?
Both. Well, we're going to write recursive functions. Right now, we're talking about the concept in general, but we're about to write a recursive function like imminently.
For microcontroller, saying that every single microcontroller is different based on the amount of inputs and outputs it can control.
Well, not every single one is different. You might have 2 microcontrollers from different brands that have the same number of inputs and outputs and the same speed processor or something that's just Nike versus Reebok or something, so. But the things that differentiate microcontrollers are very similar to the things that differentiate cars or the things that differentiate any other gadget that we buy in life. Some can do more or less than others, but something that does less than another one, as long as it does enough, it's good enough. We're not going to notice a difference. And that's really the position most of us put into a lot of stuff we buy. Computers, being in a computer science class, this is the place where it's most obvious where, when we go out and buy a computer, we usually buy the fastest processor we can afford, or the most amount of RAM we can afford, or the biggest hard drive that we can afford. you can decide how you want to prioritize those things depending on the kind of things you're going to do. But in almost every single case, we buy, unless you have a real specific thing you're building for. In most cases, we buy way more power than we need for, and we could have actually saved money and not realized any difference in performance. Because our CPUs sit idle 95+% of the time. Even when you're playing a video game, sure, you have your super expensive machine that can maintain, 200 frames a second, faster than your eyes are ever going to be able to see, more frames per second than most of our monitors can even show, yada, 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 whatever it is. But realistically, you're probably not going to drastically notice the difference between 200 frames a second and 90 frames a second on your computer. Drastically. But the price difference might be $1,000 for that GPU. You can go out right now and buy a NVIDIA 5060, which is the lowest end of the highest end, and that's like $300-ish for a 5060. Or you can buy an NVIDIA 5090. How much is an NVIDIA 5090? Yeah, $2,500 to $3,000,
Yeah.
something in that ballpark. 300 versus 2,500, and you might not notice the difference. That's a lot of difference in money, right? Now, if you just have money pouring out of the pocket, like, I'm just always going to buy the best. I don't care if I'm not going to need it. Just, I want the best. That's fine. You're choosing that, but it's rarely what we actually need. Okay, and as computer scientists, we might be able to go in with our homework having already been done. Sometimes you're also thinking about future proofing, right? Sometimes you might say, okay, I'm buying this computer. This is a lot of money for me. I plan on this being my computer for the next 5 years. Maybe then you say, okay, instead of spending 300, I'll go ahead and spend 700 on the better GPU because it's going to stretch out my usable years by a couple of years, something like that, especially if you're a gamer. You might want to overfit so that you don't have to replace that as often. But in any case, we always want to use the right tool for the job. So I don't want us to view recursion as a better tool. It's just a different tool. Okay, so recursion is when we have a function that calls itself from within itself. Now on this slide right here, I'm going to go ahead and put the upside and the downside, and then we're going to experience this. So pros. Let's see. Let's call this benefit. Solutions are often shorter and more elegant looking. Elegant is going to be a pretty loaded word there, but just let it be. It's fine. Problem uses way more memory. So we would say that recursion in general is memory inefficient. And we're going to talk about why here in a second. All right. So I'm kind of giving you all the punchlines, and then we're going to go back, fill in the proof, the evidence. Go ahead. Not a new variable. You have to put the entire function on hold so that you can wait for the new version of the function that you called to finish before this guy can continue. So this has to be paused, and let's say you have a function with 20 variables in it. All 20 variables need to be stored somewhere, the current state of them, because later on you're going to come back and reload this version of the function. Well, not just variables, also the framework of what it takes to hold a function together. If we think of ourselves as a creator, and you're the creator of a programming language, somewhere in your creation, you're going to build the ability to generate functions. Functions have a return type. Functions have a name. Functions have a parameter list. May or may not have types associated with it. Functions have a body. What's the body? It's a statement. Well, a statement often is a collection of statements. When we look at our code, Java, we usually have an opening curly brace and a closing curly brace. When you look at Python, you're indented, right? Well, all that crap in the indentation or all that stuff in between the opening and closing curly braces, though that is a single statement in that programming language called a block statement. A block statement is a little container that holds a bunch of statements, including other block statements. All right. So now you have this giant bag of statements. Bottom line is when you implement the idea of creating functions in a programming language, that's a fairly hefty data structure. The thing that allows functions to exist, let's just say, weighs 20 pounds. Just giving ourselves a real example. So I have something that weighs 20 pounds. Now, when I'm making a recursive call, so I'm going along, a recursive call is when a function calls itself from within itself. I'll add some details to that here in a second, but just I'm a function A, and in the middle of me doing my logic, I might call myself with some different inputs. And I'll wait for the result of that call to myself before I can continue. So if I weigh 20 pounds, as soon as I call myself, I'm effectively saying, okay, operating system, I need you to pause me for now because I need this call to myself to finish before I can continue. So that means the operating system is going to take your 20 pounds and throw it on the shelf. Well, now the next version of you comes along and it's going to get to that same line of code where and maybe again, it's going to call itself, right? So now it's like, okay, well, that version needs to wait for that guy to finish. So we're going to put another 20 pounds on the shelf over and over and over again. Finally, we hit the end case for our recursion where we don't make that call to that line. We no longer have to call ourselves anymore. We have finished doing whatever we're doing. And we'll look at a real example in a minute. Okay, so what does that mean? It says, okay, well, that means we have an answer here. So that means I can take this 20 pounds off the shelf and I can finish this guy. Then I can take this 20 pounds off the shelf and I can finish that guy. Then I can take this 20 pounds off the shelf. That shelf had to hold a bunch of weight, right? Okay, that's the inefficiency of recursion. Okay, instead of weight in terms of lifting, it's memory, right? We have to store that somewhere. Okay, and since it's during runtime, that's going to get stored inside of system memory. This is where your 16 gigabytes or 32 gigabytes or 48 or 64 gigabytes of system RAM comes in. You could crash your computer real easily with a programming language that doesn't run inside of a virtual, at least a virtual environment. Why? If you have a computer with 48 gigabytes, I can just write an infinite loop in a programming language that doesn't run inside of a virtual environment and just keep calling the function over and over and over again recursively. Before long, I'm out of memory in the middle of my program running. Because every single time I made a recursive call, I had to put that first call, that 20 pounds, on hold. And even if you have 64 gigs of RAM, you can only hold so many 20-pound weights before you run out of storage, right? You can't carry more than 64 gigabytes of that data. Now, most of our modern programs in our operating systems, when you double click on a program, it runs inside of its own little virtual pod that usually associates a maximum amount of memory to it. So in that case, what you would end up happening, like in Java, you get what's called a stack overflow exception. And we'll actually look at that here in a second. I'll cause that. But that means that, look, I gave your program 50 megabytes of memory, which for a program, that's quite a bit of memory, even though we think of things in terms of gigabytes. And you zipped right through that. And so now we are out of space. So either there's something wrong with your code or the problem you happen to be solving has a larger memory requirement than we by default give you. So then when you run it, you can give command line arguments to Java to say, give me 7 gigabytes of memory to work with, an amount that you think is more appropriate for the problem you're solving or whatever. So you can do these types of things. So we're mostly protected from ourselves these days. But this was actually the best learning process when I was first learning to program. We didn't have anything like virtual environments and stuff like that. So I started learning in C. So it was fairly often. I mean, think about the number of errors, the number of mistakes you're making as a beginning programmer, right? I made those same errors. You know, it's not like I just came into existence and could just write this stuff. I had to learn to do it. Okay. But the consequence used to be your computer would crash and you'd have to restart the operating system because you'd run out of memory or something. Like literally, you had to turn your computer off and on again in the middle of your homework to continue on. All right. Was there a question? Go ahead.
Are you like constantly attributing memory to the variable that's being changed? That by
Yeah. So let's get into it. So we actually see this. So let's look at a problem that by definition is recursive. All right. So let's look at the factorial problem. So if we have factorial like 4 factorial, 4 factorial is equal to 4 times 3 times 2 times 1, right? So 4 times 3 is 12, 12 times 2 is 24, 24 times 1 is 24. So 4 factorial is equal to 24, right? All right, so we can write this iteratively, no problem. Let's just jump into our language here real quick. Let's see, do I have, what language am I doing here?
No.
Remember, hold on. Remember, the language doesn't matter. So we could pick scheme if we want.
Let's use Lua.
No, okay. I'm not going to get that much off topic here, but just trust me when I say Python's a pile of crap. Okay. No, but here's the rationale. Python is a language that is used by a whole bunch of people in the world who are not programmers. That doesn't mean Python doesn't have a place, but Python takes too many shortcuts such that you have less control over your performance by default based on the code that people are often copying. I know a whole bunch of people in the data science world who what they will do, and they're good at what they do. You know, they have some giant data set somebody gives them access to. So what they do is they go and say, I'm going to copy this code, this Python code. I'm going to drop in here. I know that this code helps me visualize data, whatever data I give it. And all I need to do is change the name of the file that's in here and then the nature of the data. I might have to describe the data. So I might copy in 100 lines of code and I'm going to modify 3 of those lines. And that might be my job, and that's okay. There's nothing wrong with that. I mean, why should that person have to learn to write all that stuff from scratch if their job is to take data and analyze it, make decisions based on the data? They're not a programmer. But languages like Python that have robust module packages where it solves all the dependencies and stuff like that. I mean, these are all great quality of life features. But when you learn that as your first language, you start feeling like, oh, that's how all languages should act. And Python, while being the appropriate language for certain things, is not the appropriate language for things that we use all the time, like embedded programming stuff and things like that. You know, the second you add an interpreted language to a dishwasher, you've increased the price of that circuit board, the programmable controller, probably tenfold. Because now you need a much, much, much more powerful processor to run the Python interpreter to interpret your program that's controlling 5 inputs and outputs. See what I'm saying? There is a right tool for the job. And while Python is great for non-programmers, and I use Python all the time. All the time. I'm not saying it doesn't have its place. Okay, most of it's the module stuff, and I do a lot of AI things. So Python ends up being the right tool for the job for a lot of things. But it's a terrible first language to learn. You know, and there's tons of pressure in higher ed to learn that. And we tried it for 15 minutes last semester, and it was garbage, and I bailed on it. It's a bad language. All right, so we're going to write this in Java. All right, so we're going to keep it all inside of main for right now. In fact, just to redo what I typically do here, I don't like that online GDB names my file main.java. So I'm going to go ahead and change this. I usually use driver. That connects the dot to an older thing, like you download software that runs your graphics card. Those are called drivers. This is the file that has main in it that will run my program. So this is the driver for my program. Now remember, in Java and most modern languages, the name of your class has to match the name of your file. So I'll change this from main to driver. All programs begin and end with main. This is what main looks like in Java, public static void main, string array args. You can change args to whatever name you want. It's for command line arguments. Maybe we'll mess with it, maybe we won't, but blah, blah, blah. This is how you write it. All right. They already put the little hello world thing in here. I usually hit run just so I could see it run. We get our hello world. Now I know I have a working environment. All right. So now we're going to go ahead and we are going to write a function that we can call that does factorial iteratively. All right. So we're going to make it static. Don't worry about that. It's owned by the class. Because of the way I'm going to call it, I'm making it static so I don't have to create instances of the class. This guy is going to return an int that is the factorial of a number. So we'll call this guy factorial iteratively. All right. And it's going to take in an integer n. So if I pass it a 4, it should do its stuff and return a 24. If I pass it a 5, it should do its stuff and return a 120, so on and so forth. All right. Now, because we know how factorial works, like 4 factorial is 4 times 3 times 2 times 1, and we keep building up our multiplication, right? Okay. So we can say something like int answer is equal to 1, because anything times 1 will be itself. So it'll get the ball rolling. And there's some more efficient ways that we could write this, but I'm going to write it in the most like obvious way that hits the full example. 4 factorial is 4 times 3 times 2 times 1. Even though we know anything times 1 is itself, we're going to still do it. We'll multiply it by 1 so we can see the full iteration of this. All right. So we're going to say while n is greater than 0, because we don't go times 0, right? 4 factorial is 4 times 3 times 2 times 1. We stop at that 1. So as long as n is greater than 0, we're going to do some stuff. What are we going to do? We're going to say answer. Answer is equal to whatever answer currently equals times the current value of n. So the first time through, that would be 4 in our example. All right. After I do that, I'm going to say n minus minus. So 4 becomes a 3. Is 3 greater than 0? Yes. Multiply my running total by 3. 3 becomes 2. Is 2 greater than 0? Yes. Multiply my running total by 2. 2 becomes 1. Is 1 greater than 0? Yes. Multiply my running total by 1. We didn't actually have to do it, but we're doing it. Okay. 1 becomes 0. Is 0 greater than 0? It's not. So we're done. We fall out of this while loop and we return our answer. All right. So this guy is called factorial iteratively. So up here, we're going to go ahead and call this. We're going to call this guy solution is equal to, now this is a static function. Static members of a class are owned by the class, and we call them using the name of the class in which they were defined. So I would say driver dot factorial iteratively 4. That's going to call this guy passing a 4 in. It's going to do the math. It's going to return. We expect it to be a 24, right? So we'll go ahead and instead of printing out hello world, we'll print out solution. We'll go ahead and run this and we get our 24. Yeah. Here's solution. Solution is the result of me calling my function on the value 4. Here's what my function does. This solves factorial. I come out here and get my solution. I could change that to a 5. Still works. 120. Now you can go through here and say, oh, well, what if it's a negative number, yada, yada. We could do all sorts of error checking and crap, but can we all agree this is an iterative version of factorial? Go ahead. I'm going to solve it recursively. Yeah, I'm showing you we can do this iteratively. In fact, any problem that we can solve recursively, we could solve iteratively with a loop and something called a stack, a data structure called a stack that you're going to learn about in coding 3, but we're going to see the error here in a few minutes when I force a Stack Overflow exception. It's not like the language itself doesn't use a stack to implement recursion. It's just doing it behind the scenes. We can just decide to say, you know what, I don't like coding things recursively, so instead, I'll code it using a loop and a stack. So effectively, I'm not making recursive calls, but I've implemented recursion myself. It's a cop-out that has all the same work associated with it. All right, so now going back to the slides here, this is one way of looking at factorial, right? We just did the iterative version of factorial. We started at the top number, we counted down to 1, multiplied through each time, and stored our result, giving our final answer, right? But if we think about factorial, we could actually define factorial in terms of itself. So for example, 3 times 2 times 1 is what? What's another way of saying that? 3 times 2 times 1. What? So 4 factorial is equal to 4 times 3 factorial. 3 times 2 times 1 is 3 factorial. 3 factorial is equal to 3 times what? 2 factorial. 2 factorial is equal to 2 times 1 factorial. 1 factorial is equal to 1. That's our stop case. We stop calling things recursively when we hit that 1 in this particular example. All right, so first time through, when I'm solving 4 factorial, I'm going to say, oh, well, the answer is going to be 4 times whatever 3 factorial is equal to. Well, I have to wait for that answer because I look around and I say, is there anybody around here who knows how to solve factorials? Oh, it's me. I know how to solve factorials. So while I'm solving 4 factorial, I need to go take a break, duplicate myself, and I have to go solve 3 factorial in order for 4 factorial to finish. And then while I'm solving through, so 4 factorial is on the bench. We just threw 20 pounds up there. Now I'm solving 3 factorial. So 3 factorial, I'm going to say, okay, well, I'm going to return 3 times 2 factorial. Is there anybody around here who knows how to do factorials? Oh, it's me. So I'm going to put my 3 factorial on hold, another 20 pounds. So now I have 4 factorial on hold. I also have 3 factorial on hold because I have to solve 2 factorial. So now I'm going to solve 2 factorial. 2 factorial is 2 times 1 factorial. Is there anybody around here who knows how to do factorials? Oh, it's me. So I'm going to put another 20 pounds up here because now I have 4 factorial is waiting on the answer to 3 factorial, which is waiting on the answer to 2 factorial, which is waiting on my current answer of 1 factorial. So now I say 1 factorial. Finally, I have an answer for you that doesn't require me to split myself into another job. It's 1. 1 factorial is 1. So now I can finish solving 2 factorial. 2 times 1 is 2. So now I have that answer. Now I can finish solving 3 factorial, okay, which is 2 times 3, which is 6. So I have that answer. Now I can finish solving 4 factorial, which is 4 times 6, which is 24. And that's the final answer I'll return. So if we want to see that in code, we would say static int factorial recursively. And this will take int n as a parameter. All right, so we're going to ask the question, if n is equal to 1, return 1 or return n. Otherwise, return n times factorial recursively of n minus 1. So up here, I'm just going to change the function I'm calling to the recursively one. The recursively function, I'm passing in a 5 here, so I know my answer should be 120. 5 comes in here. We ask the question, is 5 equal to 1? Nope. So I'm going to go ahead and return an answer. What answer am I returning? I'm returning 5 times whatever factorial recursively returns for 4. Put 20 pounds on hold. Because I can't, this call to factorial recursively cannot finish until I have my answer of what's highlighted there. So first, let's see it run. So we see we still have our 120. So that's a recursive version of that guy. I'm calling this guy right here up here. So factorial recursively calls himself from within himself. That is the definition of recursion. When a function calls itself from within itself. And when would it do that? Well, a function, we are calling the function that knows how to do factorial whenever we need to do a factorial, even though we're right in the middle of solving a factorial. Does that make some sense? It is hard to get your mind to start thinking that way. But when you think of things like objects, you could say, okay, I have this widget here. Just go, oh, Christian worldview, Holy Bible, right up there. All right, so I have this widget here. Should we call the Bible a widget? Probably not. All right, so we have this widget here that if I toss it a number, it'll give me that number factorial. Okay, so I pick up this widget and I say I need 4 factorial. I need 5 factorial in the current example. So I need 5 factorial. Yeah, no problem. I'm going to go ahead and give you 5 times 4 factorial. So I'm going to need you to hold on for a second. Locks everything down. Now I have to call that same widget again. I got to put this guy up on the shelf. I bought several of these from Home Depot, so I'm good to go. So this guy, I'm going to make it disappear from the shelf. It's not on the shelf anymore. Now I got a brand new one sitting here. It's like, oh, but I need to solve factorial. I actually need 4 factorial because the guy on the shelf says, okay, the answer is 5 times 4 factorial. Well, now I need to pick up my machine here that knows how to figure out factorials. It's called factorial recursively. So I drop a 4 in there. He says, oh, the answer is going to be 4 times 3 factorial. So I'm going to put this on the shelf. And I'm going to go back to, he's like, oh, I need to solve 3 factorial. Do I have anything that can solve 3 factorial? Oh, right here, this widget knows how to solve 3 factorial. So I'm going to put 3 in there. This guy says, okay, the answer is 3 times 2 factorial. Well, crap. So I'm going to put this on the shelf. I'm going to go back over here and says, luckily, I have another one. So I need to solve 2 factorial. All right. So this guy says, yeah, the answer to 2 factorial is 2 times 1 factorial. Well, crap. So I'm going to put that on the shelf. I have one more, luckily. So I need to solve 1 factorial. So I pick this guy up and says, can you please tell me the answer to 1 factorial? Yes, the answer is 1. Ha! I got an answer out of this thing. The toast finally popped. Right? So I got my answer of 1. Now I go back over here and I say, okay, well, now that I have 1 factorial, I can go and grab my widget and say, oh, I got 1 factorial. What's your answer now? Oh, the answer to 2 factorial is 2 because 2 times 1 is 2. Great. Now I have 2 factorial. Well, this guy's waiting on 2 factorial. So I'm going to go ahead and reload him and say, okay, I have 2 factorial for you. Can you tell me what 3 factorial is? Sure, I can finish the job now. That's 3 times 2, which is 6. So it gave me a 6. Ah, okay, so I have 6. So now I have 3 factorial. I'm trying to solve 5 factorial. So I have 3 factorial. What can you tell me? Okay, so I have, this is 4 factorial. So 4 times 6, which was the answer of 3 factorial, is now 24. I have 24 as my answer for 4 factorial. Okay, so now, oh, I have one more guy on the shelf, 5 factorial. He's waiting for my answer to 4 factorial. So I throw that in and he says, ah, the answer is 5 times 4 factorial. 4 factorial was 24, so 5 times that is 120. Finally, I have my answer. The shelf is now empty. I've brought back all the recursive calls. I finally unwound the recursion and I have my final answer of 120. That makes some sense? It will be difficult for you to get your mind to think recursively, which is why the first problem we're going to pick to solve recursively is something called MergeSort, which will destroy your soul. Christian worldview. Because here's the quick scoop on MergeSort, and we'll talk about the details of it next time, and then it'll be your homework over the weekend. You might want to start thinking about it now. So we have MergeSort. Now I'm going to just give you the high level version of MergeSort since we only have a few minutes left, okay? But we'll go into the details. I'll start from scratch next time, but let me just give you the high level scoop. So MergeSort says, give me a list of unsorted numbers, or at least numbers that are not necessarily sorted. So I have this list of numbers. So what I'm going to do is I'm going to look at this and say, are you sorted? We're going to say no. I'll explain how we know whether something is sorted trivially next time. I'm going to say no. So what do I need to do? Well, MergeSort presumably sorts data. That's what that guy does, right? So I make my first call to MergeSort on this entire collection and it says, oh, that's not sorted. So what do? I'm going to split it into two halves. I have this half and I have this half. I'm going to call MergeSort on this half and I'm going to call MergeSort on this half. Because MergeSort knows how to sort crap. Okay, so I called MergeSort on this half first. The second call to MergeSort was when I called it on this half. So this guy's going to be waiting a while because we have to wait for this entire half to do its thing before we even get to that original second call. Because I get to my MergeSort call on just this half. We say, is this sorted? Nope. So what do? I split it in half. Called MergeSort on this half, called MergeSort on this half. Is this half sorted? Nope. So what am I going to do? Split it in half. I'm going to call MergeSort on this half. This is a one list. And I'm going to call MergeSort on this half. Is this sorted? Yes, because there's only one element in it. By definition, it's sorted. Is this side sorted? Yes, because there's only one element. By definition, it's sorted. So I'm going to pop back up and I'm going to do my merge step. I'm dealing with a two list here. I'm going to merge those two numbers together so they're in the correct order. And I'm working with pointers here, so it's actually happening to the original. We'll cover that. So now I've sorted this two list, and we can bounce back up, and now we can do the two list, the second call to that two list. Boom, boom, sort that guy. Now I have this four list sorted. I've merged them. I can pop back up. Now I get to my second call over here, and it starts going down, sort. Finally, I get back to my original call. Here's my two lists. I merge these guys back together, and I have my sorted list. That's MergeSort. We make two recursive calls, one for the left half, one for the right half. Whew. What do you think?
That's a more efficient way of doing it.
So the question for the online people was, is this more efficient? The answer is it depends. First of all, efficiency means different things, right? But just generally speaking, in 10 seconds as we're out of time is, yes, if you have multiple cores or multiple threads that run on multiple cores. So even though recursion is memory inefficient, if we can split the work up, nothing says that I can't sort the left half and the right half at the same time, right? Straight recursion on one core says this guy has to wait for this whole side to finish. But when I'm dealing with multiple cores, all that's required at this top level is I have two sorted halves. If I could say core one, you sort this half, core two, you sort this half, they all do their job. When we come back up here, our final step is just to merge them together. So when you have multiple cores, they would get higher performance. Sound good? All right, questions, oh, go real quick. Yeah. Because a list that has one thing in it is trivially sorted. MergeSort's based on that. We will put real numbers to this next class and see it go down, and then you are writing it. All right? So in the meantime, I might challenge you to go home and try to write the factorial iteratively and then recursively, just kind of solving it yourself. It's a small enough problem. Don't copy my code. Just to kind of get into the Java flow of things and the recursive flow of things, because I promise you your weekend is ruined with MergeSort. It's going to be the hardest thing you've ever written. Trust me, there is a reason behind my madness.
ChatGPT thinks that
Yeah, this is the key to ChatGPT problem, right? that hug.
Brady, I need to put it,